determine the appropriate feeder size for supplying power to a panel serving multiple air conditioning units, you can utilize the minimum circuit ampacity values. In this scenario, you have two 5-ton air conditioning units, each with a minimum circuit ampacity of 35 amps and a maximum breaker size of 50 amps, and one 4-ton air conditioning unit with a minimum circuit ampacity of 24 amps and a maximum breaker size of 40 amps. The initial calculation involves summing the minimum circuit ampacities of all three units, resulting in a total of 94 amps, 35 amps plus 35 amps plus 24 amps equals 94 amps. A 100 amp feeder, as calculated, proves adequate for the 120/240 volts one-phase feeder to the panel. The rationale behind this lies in the fact that the circuit amperage figures employed represent the minimum ampacity requirements as stipulated by the National Electrical Code, NEC. These values are derived from the full load current of a compressor and fan motor, incorporating a safety factor of 1.25. This safety factor ensures that the feeder is capable of handling the increased current draw during startup and other demanding operating conditions. By basing the feeder size calculation on the minimum circuit amperage, you ensure that the feeder is sized to safely accommodate the maximum current draw of the air conditioning units. While the nameplate ratings of the air conditioning units may suggest larger breaker sizes such as 50 amps and 40 amps, the actual operating current is likely to remain below the minimum circuit amperage, particularly under normal operating conditions. This is because the minimum circuit ampacity already incorporates the necessary safety margin. It's important to understand the difference between the minimum circuit ampacity and the maximum overcurrent protection, or breaker size. The minimum circuit ampacity determines the minimum allowable ampacity of the conductors, ensuring they can safely carry the expected load. The maximum overcurrent protection, on the other hand, protects the conductors from overloads and short circuits. The NEC provides guidelines for selecting both the conductor size and the overcurrent protection, and it's crucial to adhere to these guidelines to ensure a safe and compliant installation. When sizing a feeder for multiple loads, such as air conditioning units, the NEC allows you to apply demand factors to reduce the calculated load. Demand factors account for the fact that not all loads will operate at their maximum current draw simultaneously. However, in the case of air conditioning units, it's generally recommended to avoid applying demand factors, as these units can operate at or near their maximum load for extended periods, especially during peak cooling seasons. Therefore, it's prudent to size the feeder based on the sum of the minimum circuit ampacities of all the air conditioning units, as done in this scenario. In summary, a 100 amp feeder is indeed appropriate for this application, as it adequately accommodates the combined minimum circuit ampacities of the three air conditioning units, while also adhering to the safety requirements and guidelines outlined in the National Electrical Code. Always consult with a qualified electrician or electrical engineer to ensure that the feeder size and other electrical components are properly selected and installed in accordance with local codes and regulations. Firstly, understanding the minimum circuit ampacity is crucial for properly sizing electrical feeders. Secondly, the NEC provides guidelines for calculating minimum circuit ampacity based on equipment nameplate data. Thirdly, the minimum circuit ampacity includes a safety factor to account for motor starting and other temporary overloads. Fourthly, the feeder size must be adequate to carry the total connected load, plus any applicable demand factors. Fifthly, overcurrent protection must be provided to protect the feeder conductors from overloads and short circuits. Sixthly, the overcurrent protection device must be sized in accordance with NEC requirements. Seventhly, voltage drop should be considered when sizing feeders, especially for long runs. Eighthly, proper grounding and bonding are essential for electrical safety. Ninthly, all electrical work must be performed by qualified personnel in accordance with applicable codes and standards. Tenthly, regular inspection and maintenance are necessary to ensure the continued safe and reliable operation of electrical systems. Now let's delve into each of these points in more detail. Firstly, the minimum circuit ampacity is a critical parameter for determining the appropriate size of electrical conductors. It represents the minimum current carrying capacity required for a circuit to safely supply power to a particular piece of equipment or load. This value is typically found in the equipment's nameplate or in the manufacturer's specifications. Secondly, the National Electrical Code (NEC) provides comprehensive guidelines for calculating the minimum circuit ampacity based on the information provided on the equipment nameplate. These guidelines take into account various factors such as the equipment's full load current, motor horsepower, and operating voltage. The NEC tables and calculation methods ensure that the conductors are adequately sized to handle the expected current draw. Thirdly, the minimum circuit ampacity inherently includes a safety factor to accommodate motor starting and other temporary overloads that may occur during the equipment's operation. Motors, for example, draw significantly higher current during startup than during normal running conditions. A safety factor incorporated into the minimum circuit ampacity accounts for these temporary surges, preventing the conductors from overheating or being damaged. Fourthly, the feeder size, which refers to the size of the conductor supplying power to a panel or distribution board, must be adequate to carry the total connected load. This includes the sum of the minimum circuit ampacities of all the individual loads connected to the feeder. In some cases, demand factors can be applied to reduce the calculated load, especially when dealing with multiple loads that are unlikely to operate simultaneously at their maximum capacity. However, it's important to carefully evaluate the load characteristics and usage patterns before applying any demand factors. Fifthly, overcurrent protection is a crucial safety feature in electrical systems designed to protect the conductors from overloads and short circuits. Overloads occur when the current flowing through a conductor exceeds its rated ampacity, causing it to overheat. Short circuits, on the other hand, are unintended paths for current to flow, resulting in a sudden and dramatic increase in current. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current in these situations, preventing damage to the conductors and equipment and minimizing the risk of fire or electric shock. Sixthly, the overcurrent protection device must be sized in accordance with the NEC requirements. The NEC specifies the maximum allowable size of the overcurrent protection device based on the ampacity of the conductors being protected. The goal is to provide adequate protection without causing nuisance tripping, which can occur if the overcurrent protection device is too sensitive. Seventhly, voltage drop is an important consideration when sizing feeders, particularly for long runs. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can negatively impact the performance of electrical equipment, causing them to operate inefficiently or even fail prematurely. To minimize voltage drop, it's often necessary to increase the size of the conductors, which reduces their resistance. Eighthly, proper grounding and bonding are essential for electrical safety. Grounding provides a low-resistance path for fault current to flow back to the source, allowing the overcurrent protection device to quickly interrupt the circuit. Bonding ensures that all metal parts of the electrical system are electrically connected, minimizing the risk of electric shock. Ninthly, all electrical work must be performed by qualified personnel in accordance with applicable codes and standards. Electrical work can be dangerous, and it's essential to have the knowledge and skills necessary to perform it safely and correctly. Improperly installed electrical systems can pose a significant risk of fire, electric shock, and other hazards. Tenthly, regular inspection and maintenance are necessary to ensure the continued safe and reliable operation of electrical systems. Electrical systems should be inspected periodically to identify any potential problems such as loose connections, damaged insulation, or corroded components. Maintenance activities, such as tightening connections, replacing worn components, and cleaning equipment can help to prevent failures and extend the life of the electrical system. In conclusion, sizing electrical feeders requires a thorough understanding of various factors, including minimum circuit ampacity, NEC guidelines, overcurrent protection, voltage drop, grounding and bonding, and proper installation and maintenance practices. By following these guidelines, you can ensure the safe and reliable operation of electrical systems.